Alright, you ready for some exciting stuff? This is going to be the second method that we can use to find the inverse of a matrix, and it's going to be the Cholesky method. Now you may have heard of this before. We used the Cholesky method in video 3.23 on triangular square root matrices. You need to know this to understand this video. We can use this method as well to calculate the inverse of a matrix. First, we adjoin an identity matrix to the target matrix A. Remember that our target matrix A is equal to 4, 6, 2, 6, 16, 3, 2, 3, 9. So what we're going to do is adjoin an identity matrix with it. So it's going to look like this. 4, 6, 2, 1, 0, 0, 6, 16, 3, 0, 1, 0, and 2, 3, 9, 0, 0, 1. And notice this is a 3 by 6 matrix. So next we're going to perform the Cholesky algorithm. We're going to essentially Choleskify this, or as it says in your text, this 3 by 6 matrix is going to be Choleskized. You can also see on page 121 of the text that the schematic design of the process kind of looks like this. We've got A, I, these are adjoined, and then we're going to have our triangular matrix here, and the inverse of a transpose, a triangular matrix, and these two are also adjoined. And both will be 3 by 6 matrices. From video 3.23 on triangular square root matrices, we found that the triangular square root matrix of this A matrix to be this. And this is just going to save us some time, so please refer to that video if you need to, but we found it to be 2, 3, 1, 0, square root of 7, 0, 0, 0, square root of 8. And as you notice, this is a upper triangular square root matrix, because in the lower triangle we have zeros as values. So what I'm going to do, just for a reference for us to make things easier as far as understanding this video, is write out notations for these values. So in the adjoined matrix of A and I, this first one for A11, then we have A12, A13, A14, A15, A16. Second row, first column, second row, second column, A23, A24, A25, A26, A31, A32, A33, A34, 35, and 36. Okay, you might thank me later, you might not. But I'm also going to do T. So for T, we have T11, 1, 2, 3, 1, 4, 1, 5, 1, 6. And our last row. Okay. Once again, we did get this T using the Cholesky method, as we see in video 3.23. And as we see here, this 3 by 6 matrix is the target matrix A joined to the identity matrix I. The bottom one is the upper triangular matrix T that is extracted by the Cholesky algorithm, adjoined to the lower triangular transpose or inverse of the transpose of T matrix that will be extracted in parallel. And this, once again, is a lower triangular inverse root matrix. So let's talk about how to get the lower triangular inverse root matrix. The formulas for the Cholesky process are, of course, the same as those used in video 3.23, but we already have the diagonal element for each of the 3 rows. That diagonal element is here, 2 square root of 7 and square root of 8, because it's T11, T22, and T33. So we only use 2 of the formulas, the one that gives the remaining elements in the first row and the one that gives the remaining elements in the successive rows, the second and third. So for the first row, the additional entries are T14, T15, and T16, and we can find them using the formula that we learned before. So we say this is for the first row. So we have T14 is going to be equal to A14 over T11, which equals A14 is 1 over T11 is 2, so 1/2 or 0.5. So T15 is going to be equal to A15 over T11. A15 is 0 over 2 is 0. And then T16 is A16 over T11, which also equals 0 over 2, 0. So let's build it over here actually. So we have our first row completed of this one. We got 5, 0, 0. Now for the second row. Using formulas that we learned previously with the Cholesky algorithm, the Cholesky method, we need T24, T25, and T26. So T24 is equal to A sub 24 minus, we've got a summation as k goes from 1 to 1, or it's actually I minus 1, and I would be 2, j would be 4. So we get 1 of t sub k2, t sub k4, this is I and j, over t sub the diagonal in this row, which is on 2, 2, which is square root of 7. So A24 is going to be this 0 minus, and then so k goes from 1 to 1, so T12 is 3, and T14 we found up here 0.5, 1/2. And like I said, that is over the square root of 7. This is going to equal negative 1.5 over the square root of 7. So we can put that in here, negative 1.5 over square root of 7. Okay, so let's find T 0.25. Using the same formula, tk5 over t22 is going to equal 1, so a25 is 1 minus 3, same one as here, and this one is going to be 0, t15, 0, over square root of 7, which equals 1 over the square root of 7. So we can put that in here. We're halfway done. Alright, t sub 26 is going to equal a26 minus the summation, tk2, tk6, or t22. What's a26? We go up here, second row, 6 value, which is 0, minus, this is t12, which is the same as above, and then t16, which is also 0, over square root of 7. 0 over square root of 7 just equals 0, and we can put that there. So we have the first and second rows. Now, because of space and there's things on this paper that I still want you to see, we're going to do the third row on this other sheet. So for the third row, we use the same formula, but we apply it to the third row. So we need to find T34, 35, and 36. So first we've got T34. That's going to be A34 minus summation as T goes from 1 to I minus 1. Now I now is 3, so 3 minus 1 is 2. So T is going to go from 1 to 2, which means, as you'll see in a second, we'll have some more addition to do. TK3, TK4 over the diagonal for that row, which is T33, which is going to be square root of 8. So we bring this out. A34 is here, so it's going to be this value, 0 minus, now we're going to have it look like this. T13 is here, so it's going to be this value 1 times T14, which we found to be 0.5. But we have to do a summation here. Now k is going to equal 2. So T sub 23 is 0, and T sub 24, which we just found to be negative 1.5 over square root of 7. So all of that over square root of 8. It's big and long. So let's reduce that here. This big long equation, negative 0.5 over square root of 8. So negative 0.5 over square root of 8. Now let's do T35, which is going to be just as long. I'll try to do this a little quicker. Excuse me, that's a T, K3, K5. So A35 is 0 minus, it's going to be 1, 0. So T13, which we know is 1, T14 T15. It's up here is 0. Add that to T23, which is 0, plus T25, which is 1 over square root of 7. And see now that as we also do this, it's going to be 0 minus 0 plus 0 over square root of 8 is 0. One more value, T36. A36 minus summation TK3, TK6, all over T sub 33. So A36 is 1 minus, we know this is going to be 1, T of 1, T16 is 0, plus T23, which is also 0, and T26 is 0. So T23, 0, T26, 0. Square root of 8, this is going to leave us with 1 over square root of 8, which is our last value here. Yay! Are we done? So when we talked about in video 3.23 on the triangular square root matrix, we demonstrated that the upper triangular root matrix T is indeed the square root of the A matrix. We pre-multiplied T by its transpose, and the resultant product was equal to A. So we did, I'll actually do it over here on this paper. We did transpose of T times T equals A. Similarly, it can be demonstrated that the lower triangular inverse root matrix, this one that we just got, is the inverse of T by executing either the following two equations and obtaining the identity matrix I as the product. So we can do the lower triangular inverse root matrix times the inverse T equals I, or you can do this one, the inverse of T times T equals I. This last one is simpler, and easily demonstrated as we talked about in the introduction to matrix inversion. This is because 1 over T times T would just equal 1, right? So it would equal the identity matrix. So let's do that one on this sheet of paper. Okay. So we're going to do this inverse of T times T and the inverse of T is 0.5, negative 1.5 over square root of 7, 0.5 over square root of 8, 0, 1 over square root of 7, 0, and then I should have made this a little longer. This is going to be 0, 0, and 1 over square root of 8 times our T, which was 2, 3, 1, 0 square root of 7, 0, 0, 0 square root of 8. And if you work this out either by hand or using Excel or whatnot, you will actually find that this is equal to identity matrix by this equation. So thus the lower triangular inverse root matrix is the inverse of T, our original T matrix. So are we done yet? Well, the inverse of the root matrix T was not the purpose for this algorithm. The purpose was to create the inverse of the original matrix A. If you can recall, So this is obtained by multiplying the inverse T matrix by its transpose according to either of the following formula, which I'll write here. We have the inverse of A equals the lower triangular inverse root matrix right here times the inverse of T, or equals the inverse of T times the lower triangular inverse root matrix in either order. And we'll use this one. So you may think I'm running out of space for this, but I'm not. Okay, we're going to do that here. So remember, this is this equation. So this is going to equal 0.5, negative 1.5 over square root of 7, negative 0.5 over square root of 8, 0, 1 over square root of 7, 0, 0, 0, 1 over square root of 8, which we found on the back of that you see here. Sorry, it's a little ghetto. And then that's multiplied by 0.5, 0, 0, negative 1.5 over square root of 7, 1 over square root of 7, 0, negative 0.5 square root of 8, 0, 1 over square root of 8. So this is the inverse matrix. We're multiplying the inverse matrix by its transpose. And when we work this out, we do get the following values: 0.603, negative 0.214, negative 0.063, negative 2.14, 0.143, 0, negative 0.63, 0, 0.125. Does that look familiar? Well, if you watched the video previous to this one of matrix inversion by the method of cofactors, that is what we got to be the value of the inverse of our original A matrix. And this can be verified that it is indeed the inverse by multiplying A by our calculated matrix and showing that the resultant product matrix is an identity matrix, as we have stated in the intro to matrix inverses and the video previous to that. So I will show that quickly. So it's going to be A times its inverse. You see up here, A is 462, 616, 3, 239. And when we multiply it by the inverse, you can do this by hand or Excel or whatnot, but it does in fact equal an identity matrix. So we know that what we got as the inverse of A is correct. So after all this long hard work, let's go over to Excel and look at everything and verify things one more time. Alright, I'm here in Excel. I know this looks probably overwhelming to you. If you watch video 3.23, some of this will look familiar to you. I just extended the matrices to include what we talked about when I wrote it down. So we have A adjoined with its identity here. Okay. Now we have T here, a regular T that we found previously, and then we have the lower triangular inverse root matrix. This is the inverse of T transpose indicated here that I wrote out here, and I wrote out the formulas for them as well. Okay, what they're going to look like. I went ahead, just for the sake of time, and did the values here just using the equations that we have up here above it. Okay, so we do, in fact, I did verify that the values that we got through Excel were the same that we did by hand. As you can see here, we have 0.5 below it. If you're looking in the function box here, this is negative 1.5 over the square root of 7. We do have 1 over square root of 7, 0, and then on the third row, negative 0.5 over square root of 8, 0, and 1 over square root of 8. I also did some other things. I just took the transpose of T, which we'll use, the determinant of matrix A, which we previously found to be 224. I went ahead and did matrix multiplication to show that transpose of T times T is in fact A. As you notice, these are the same. Okay, I went ahead and put the inverse of T in, which we verified was that. And what we did to verify that, we took that times the T matrix, and I'll do that here. So the inverse of T times our T, which is here, and we should get an identity, which we do. We also talked about how the lower triangular inverse root matrix here times the transpose would equal the identity. So let's do that here. So just matrix multiplication. Take this matrix times the transpose of T, which is over here, Control Shift Return, and we also get an identity matrix so that we know that everything is correct so far. Now lastly, we mentioned you can use this formula that's down here. That what we want to find is the inverse of the original matrix A, and we use the formula that is obtained by multiplying the inverse matrix of T by its transpose, which is this lower triangular inverse root matrix. So let's do some matrix multiplication. So this inverse, comma, this one that we found over there, and we get those values, which are equal to the ones that we did by hand. If I extend it out here to 3 decimal places, we'll see that. Alright, and we can verify that that is correct by doing A times the inverse of A. And what should we get? That's right, we get the identity matrix. This is, I know it's a lot to look at, but I hope it makes it a little bit easier for you, and also confirms what we did by hand over here. And that was matrix inversion by the Cholesky method. I hope you had a lot of fun. I sure did. Y'all have a great day.